Okay, we're back. Now, what are we doing? We're looking at section 3 on quantum mechanics, and we're going to plug some holes. I think I started to do this a couple days ago. So let's look at several things, okay? Some of this will be familiar to you because of middle school. How many people studied the electromagnetic radiation spectrum in middle school? Okay, some of you did, some of you didn't, okay. The electromagnetic radiation spectrum is essentially light. Light travels at 3 times 10 to the 5th kilometers per second, 3 times 10 to the 8th meters per second, or for you Americans out there, 186,000 miles in a second. If you set up optic fiber around the equator, which is 25,000 miles around, what's 186,000 divided by 25,000? 180, about 7, right? 7-ish, 7.5 maybe. You know, take off some for optic fiber interference maybe. What'd you get? You didn't do it? Okay. You about 7-ish, right? Let's say 6 maybe because optic fiber. So in 1 second, it'll go around the Earth so quickly. Yes? Divide 250,000 by 186,000. Divide 250,000 divided by 186,000. What is it? 1.34. So it takes 1.34 seconds to get to the moon, which is about 250,000 miles away-ish, right? So it takes how long? 1.3? 1.3 seconds? So what's the round trip? 2.6 seconds? Right? And they did experiments on the speed of light based on the moon and the known distance of the Earth from the moon. How about the sun? How many miles away is the sun? I know we're working in miles, I know, because I know that very easily. The sun is 93 million. All right, so divide 93 million by 186,000. 93 million by 186,000. Yes, Mouse?
8 minutes. 500.
500 divided by 60 is? 8 minutes. How did he do that? 8 minutes. Yeah, 8 minutes. It's about 8 minutes. So if the sun dies, you have 8 minutes. It's all right. I'd get out my lawn chair and go on the roof and watch it. You know, I wouldn't hide somewhere. You know, it'd be kind of fun. Get a, a nice sandwich. You know, a cup of coffee. Ooh, Kamal, excellent. How would we know? Ooh, I don't know. You got a message and you sent it faster than the speed of light, which is impossible, right? So you wouldn't know. Excellent. How would you know? That's right. How would you know? Which leads me to my next point, that matter can't go faster than the speed of light. Nothing can go faster than the speed of light. There are some experiments being done, and there's arguments to the contrary, but nothing's been, there's nothing that can go faster than the speed of light. So anyway, so electromagnetic radiation is in waves. These waves have structure. We talked about this crest, trough, amplitude. No! Made him jump. Amplitude. Yeah! Loudness. Okay, if you're talking about sound or intensity. Now let me ask you this. Ava, can you bring that book up, please? That your notebook there? Yeah, the ugly lime green thing in front of you. Bring that up. You don't have to go on camera. Just come up here. I just have something to show you. This is a little weird. I know. It's like she's like struggling to stay off camera. No, not that. Okay. Let me tell you something. How many people have ever seen, maybe in Europe or the United States, I haven't seen them much around here, but emergency vehicles that have that disgusting lime green color to them, or vests with that lime green? How many people have seen that? Raise your hand. The entire class is raising its hand except for Genevieve. She's too good for that. No, she's fine. Yes, it's Colorado, they have them, right? You've seen him in Jordan? She hasn't seen him in Jordan. Anybody seen him in the Middle East? Here? Okay, UAE, they have them, okay. I haven't seen a lot of emergency vehicles. People don't get sick a lot here, do they? They do? Yeah, I haven't seen a lot of emergency vehicles. In New Jersey, they're all over the place. Anyway, I was on a squad. I was an EMT in New Jersey. This is a story. I'm telling you a story. I was an emergency medical technician. They called it an EMT. And I was what they call basic EMT. I took care of the patient. I couldn't administer really any medicines or anything. I just took care of the patient, wounds, oxygen, make them comfortable, assess the problem, write it down, not diagnose. I would just take notes and things like that and take care of people. And we had an ambulance. We had two ambulances, and we had an emergency vehicle that went to car accidents and got people out of cars, with the jaws of life and all those other instruments, etc. You understand what I'm saying? It was an emergency vehicle. And we were getting a new one. And it was about a year and a half planning what to put in it, the dimensions, make sure it can fit in the garage that we have, etc. Okay? And there was a British gentleman, Paul, who was kind of in charge of it. And then he said to everybody, he's from England, and he said, it has to have a chartreuse stripe on it. And people are like going, yuck, what's that? Well, this is kind of like chartreuse. You've seen this, right? Kind of ugly. And everybody said, no, we don't want that. We want our colors, hunter green, very manly looking hunter green. We want hunter green. And I'm like going, wait a second. Paul's right. There's physics to support that. Does anybody know the significance of this color?
It's the most visible color.
It's the most visible color. Why?
I'm not sure.
Well,
It's in the middle of the spectrum.
it's in the middle of the spectrum. Good. What does that mean? Can I draw a graph right here? Can you see this on the thing? Can you see it? Can you see this?
Yeah.
Red, orange, yellow, green, blue, indigo, violet. Can you see that? I'm going to check. Okay. So if that's the spectrum, and this is intensity, it goes like this. About there, and about there.
It's parabola.
Yeah, it's about like that. That color there. That color is chartreuse. That's the most dominant color from the sun. So our eyes evolved to see that really well. We don't see red very well. We don't see red very well. We see violet. We don't see it hardly at all. Matter of fact, the sky is not blue. It's cyan. Cyan's kind of bluish color. I mean, it's cyan. I'm sorry. It's not. Sorry, it's not cyan or blue. It's actually purple. It's purple colors, violet colors. That's what the sky is. Yes.
Isn't the sky just like a reflection of the ocean now?
Is it what?
Or kind of like the ocean reflecting onto the sky?
No.
That's what my old
It's the other way
teacher
around.
told me.
No. They're asking me, is there a relationship between the ocean and the sky? And the answer is no. The answer is not really. But I'll answer the question in a moment. Okay? I'll answer your question. But that's why there's physics behind it, and they said, okay, we'll have the stripe, because it's a matter of safety. It's not a matter of aesthetics. Yes, the emergency vehicle looked good, but got into an accident because it couldn't be seen clearly. Doesn't sound good, does it? Ugly is better. Personally, I hate this color. I mean, it's gross, right? Because we see this so well. Now, the In tropical areas where the water is there's not much in it, there's a lot of fish, but there's not a lot of plankton in it. Unlike northern waters that are like soupy looking because it has so much life in it. I'm talking about like southern tropical waters where the bottom of the water is shallow and it's white sand. The light rays go in and then they're bounced back out. And what happens, you know what the water does? The water, yes,
Refracts.
sort of. He says, does it refract? And yeah, it does, but that's not why it's blue or cyan. It's cyan because, it's not because of the sky cyan. It's because when the light goes in, the three primary colors of light are blue, green, and red. Goes in, and the water absorbs the red. And what comes out is blue-green. What does blue-green light make? Cyan. Cyan. Color of the sky, cyan. Yeah? So people are confused. People say, well, the water is blue because of the sky. Well, why isn't deep water blue? Because of the sky. So something's a little weird. So, but that's why. The sky is blue, or appears to be blue, for different reasons, which we're going to talk about now. Okay? But let me finish up. I'll do that on the next tape. Okay? Part 4, I think we're on. This is part 3. So, these are long waves, radio waves, microwaves are here. Visible light is actually a very small portion of the electromagnetic radiation spectrum. Electromagnetic radiation spectrum. It's actually a very small part of it. Yes? Do you understand that? It's a very small part of the spectrum. Yes? But it's the one RIC. Some bees will use ultraviolet light. Yes? Yes. So, different organisms evolve differently. But we use visible light. Yes? And this is infrared light, which is heat. Heat. Microwaves, heat. Ultraviolet from the sun, not good for you. Get cancer. X-rays, gamma rays, very high energy, not good. What microwaves, look at where microwaves are. They're next to radio waves. Microwaves are very long, not very energetic. But why are microwaves so damaging? What can happen with microwaves? What's so special about microwaves? Well, you see this molecule? Excuse me. Water, H2O. HOH, 109.5-ish, right? That molecule, the structure of that molecule, the makeup of the bonds, it loves to absorb microwave energy. If you put a plate in the microwave that has no water in it at all, will it get hot? No. The microwave oven works by heating the water, and then the water heats the what? Yeah, it works through radiation. How does the food get hot? Through radiation and conduction. What does that mean? Radiation and conduction. Okay. Is the sun hot? Do you feel the heat of the sun? No, you don't. You do not feel the heat of the sun. If you go out in space, isn't it cold out there? Why isn't it warm out there if the sun's so hot? No. The light rays of the sun heat the earth through radiation. In other words, the light rays come through our atmosphere to the planet, are absorbed by material, and converted to infrared energy. See that? The infrared energy is heat. So the short wavelengths of the sun come through our atmosphere, right? And then long waves are produced, and those can't get back out. It's called the greenhouse effect. The greenhouse effect is actually important. If we didn't have the greenhouse effect, the temperature on Earth would be 50, 60 degrees colder. The problem is we have too much greenhouse effect going on. We have too much carbon dioxide. What's more dangerous, carbon dioxide or methane as a greenhouse gas? Methane is far more dangerous than carbon dioxide. People don't really talk about methane much. They talk about carbon dioxide. Where's the methane? Why is there so much methane? Well, the methane is underground, under the water, and will stay there as long as the ground is cold. It won't be released. But as soon as the ground starts to warm up, you're going to release all of this methane from prehistory. And there's a lot of methane. Remember the BP disaster in the Gulf of Mexico, all the way down? You had these giant frozen balls of methane. Amazing. Yeah. So methane can be released, and it could literally bake the planet as a result. Because the long wavelengths are coming in. Long wavelengths are coming in. They're being converted to invisible light, because you can see it. Why is it visible? Because you can see it. It comes in, you convert it to long waves, then the long waves can't get out. They're trapped. Our atmosphere will trap them. Yes? You get it? It's called the greenhouse effect. So the microwave works through radiation. It absorbs the microwave energy, then converts it to infrared energy, and then that infrared energy is conducted throughout the material through possibly convection. So you have all three. You have convection, conduction, radiation going on in there. The sun heats our planet through radiation. It doesn't do it through conduction. We don't know that the sun is hot. So when you say the sun is hot, that is actually incorrect. The sun is bright. It heats through its brightness. We obviously know the sun is hot. Yes, of course, blah, blah, blah. But it actually heats the earth through its brightness. So you say, oh, the sun is very bright today. The sun isn't hot today. The temperature of the sun doesn't change. Cloud cover, right? If you have a lot of cloud, is it a little cooler? Generally, unless you have tropical air coming up from the south. I live in New Jersey, and we have these tropical air masses coming up from Florida, and it gets very warm and hot and sticky in the summer. Rivals here. It gets 100 in the 90s, very, very, very high humidity. Awful. For like 3 or 4 weeks in the summer, living in New Jersey, unbearable. It's worse here. But in New Jersey, you'd be amazed, because you can also get a 4-foot snowfall. We got one a few years ago. Amazing how much snow. The picnic table in my backyard was gone. Couldn't see it. My dog, I had this like husky kind of wolf kind of looking dog, and she was white, and I couldn't find her out back. Couldn't find her. And I'm walking around, where is she? She pops up out of the snow. Okay, so we have these long waves going into short waves. We have lambda, wavelength. Frequency is nu. C is the speed of light. We have, it's going to be an indirect relationship. As this goes up, this has to go down, if you're going to keep that as a constant, because that doesn't change. If that's low, that's high. If that's high, that's low. Indirect. So the constant is 1 here. It can be anything, m, whatever you want to make it. Why do I say it can be m? Because you're used to linear relationships having the constant written as m, because m means what? The slope. It's actually the constant. So this is 1, this is a constant, 1 equals y over x. Yes, you remember it like this? Yes? That is the same thing. When the variables form a quotient constant, that means that it is a direct relationship. Yes? When it forms a product constant, that means that it is an indirect relationship. Now, this is really what happens in a nutshell. This is quantum mechanics in 3 sentences or less, okay? Quantum means, a quanta means packet, little packet of energy. The atom, do you realize, is extremely organized, extremely organized, extremely organized, extremely organized, very predictable. It's unbelievable, right? So what happens is if I shine energy on an atom, the electrons will become excited and it will move to a higher energy level. Quite randomly, you know, you get this random amount of energy doing that, right? And then what happens is that electron will fall back. But you see that that's a predictable amount of space that falls back. It's predictable, yes? Because of the structure of the atom is predictable. So the amount of energy that it gives off, low energy absorbs energy, high energy falls back, gives off a quantum of energy, a little packet of energy. That energy has a wavelength. That's light, lambda nu. So that has a certain wavelength of energy. It could be red light. If I take strontium and I put it in a strontium salt, and I take it and I put it in a flame, it turns brilliant red, fire engine red. If I do lithium, it's like magenta. If I do copper, it's green. So these lights are a result of these quanta of energy producing electromagnetic radiation. Correct? Electromagnetic radiation comes from this. So light, the origin of light is electron transitions. You get it? The quanta. It happens all around us. We see colors, dyes, light bulbs. It's all the same. An element, for instance, hydrogen. Hydrogen will give off 4 specific colors of visible light. Very specific. If you look at the radiation spectrum, you know what? We'll do that on the next one. Okay? I'll show you that. Okay? And that's called atomic spectra. All right? Let's finish this up. Good. Are we done? Yes? Cool about the colors of the ocean, the sky. Oh, we didn't talk about the sky. Now, you see this? You see this? Yes? Well, what happens in the sky is the elements in the sky that make up the sky, the atoms that make up the sky, the air, the atmosphere, don't they get excited? Isn't the sun energy? Don't they get excited, those elements? Yes? They get excited? Well, the light they give off, Lizzie, is what we see. You ever see a sunset? They call it a Velázquez sunset. Velázquez was a painter in Spain, 16th century something, I don't know. He was like a court painter, beautiful. They call it Velázquez sunsets. I don't know how to say it in Spanish, but there's a famous Spanish expression where it comes from. Very colorful. Well, those are different pollutants in the air will cause very beautiful sunsets. But those beautiful sunsets oftentimes are caused by pollutant particles, sulfates, phosphates, chemicals, elements. Brr. So if you say a beautiful sunset, it could be the sign of a poisonous air mass. Red sky in the morning, sailor's warning. Red sky at night, sailor's delight. What does that mean? Well, it has to do with this. You see? So the whole idea of light. See, the ocean is blue for a different reason. The ocean is blue because it absorbs the red light and kind of like scrubs the light, scrubs the red out of it. So what's reflected back out of the water is blue-green light. But the sky specifically is cyan looking. It's actually purple, but we can't see purple very well. Violet, you call it violet, okay? Because of this. They're going to homeroom. They're getting kind of itchy. Wonderful class. Wonderful. Ellen, how you doing back there? It's like she's in another time zone. She needs to have her passport checked when she comes to the front of the room. She's so far in the back. I feel like I'm teaching in Yankee Stadium. You don't know what this room looks like. It has multiple tiers, bleacher seats. It's unbelievable. Have a good day.